Hi everybody and welcome back. In this notebook we will create the three-dimensional unit for liver and liver tumor segmentation. To do so, I have already copied the code for the two-dimensional unit from the previous lectures. Regarding the necessary libraries, we still only need PyTorch. Alright, let's get started. At first we replace the two-dimensional convolutions in the DoubleConv class by three-dimensional convolutions. Next, we need to use three-dimensional max pooling instead of two-dimensional max pooling. After that, as we now have a volume instead of single slices, we need to use trilinear upsampling instead of bilinear. And last but not least, we need to increase the number of output channels from 1 to 3 to make sure our model is capable of handling background, liver and liver tumors. As three-dimensional convolutions have much more parameters than their two-dimensional counterpart, we additionally reduce the number of filters in the DoubleConv layers to decrease the network size. In DoubleConv, we now replace conv 2D by conv 3D. That's all. We introduced the three-dimensional convolutions. Next, we change maxpool 2D to maxpool 3D. After that, we use trilinear upsampling in all three upsample layers. Last but not least, we increase the number of output channels in layer 8 from 1 to 3. Of course, we also have to use a three-dimensional convolution here. Let us now reduce the network size by decreasing the filters for all DoubleConv layers. As an example, we could simply halve them. Therefore, the first DoubleConv layer would have 32 instead of 64 channels. Thus, the in channels of the subsequent DoubleConv layers are also reduced to 32. Its number of out channels would now be 64. When continuing the strategy, the third layer now has 64 in channels and 128 out channels, and the fourth one has 128 in channels and 256 out channels. Of course, we also have to adapt the up convolutional layers and the skip connections. Alright, our model adaptation is complete. Perfect! We should now create an instance of this model and test it on a random input to make sure everything works. Let's use torch.randn to generate a random three-dimensional volume. In fact, this tensor actually has 5 dimensions. First, the batch channel, next the image channels, and last but not least, the actual volume. We are now ready to compute the output of the model based on this random input. Additionally, let's make sure that the output's shape equals to a torch.size object containing 1 batch channel, 3 image channels, and 128 times 3. If that's the case, then our model should be able to predict background, liver and liver tumors. Perfect! It didn't throw any exceptions. Our model works as supposed. As usual, let us copy this code to a separate Python file. Let's call it model.py. Alright, our model implementation is complete. During the next lectures, we will implement the training routine. Thanks!